Hello everyone. The paper I'm presenting today is Mastering the Game of Go Without Human Knowledge from Silver and Ali, a paper published in Nature in 2017. The goal of the work in this paper is to develop an algorithm that tabula rasa reaches superhuman performance in a challenging domain, such as the one of Go game. Basically, an algorithm that is based only on reinforcement learning, without human data, without human guidance, and with no domain knowledge beyond the game rules. Basically, AlphaGo Zero becomes its own teacher by exploiting self-play techniques. Why using deep neural networks trained by reinforcement learning? First of all, because expert data, which is data coming from games played by human experts that can be used for training, is often expensive, can be unreliable, or sometimes even unavailable. Even when this kind of data is available, it may impose an upper bound on the performance of the systems that are trained with it. Reinforcement learning systems are trained from their own experience, in principle allowing them to exceed human capabilities, and also to operate in domains where human expertise is lacking. The problem with this kind of systems is with the most challenging domains in terms of human intellect, that require precise and sophisticated look-ahead in vast search spaces. An example of this kind of domain is the one of Go game. There are some characteristics of AlphaGo Zero that is important to understand before diving into the details of this method. AlphaGo Zero combines a self-play reinforcement learning algorithm that is used to train a neural network. There is this neural network used for function estimation that, given a board state, is a policy network because it predicts move selection, and is also a value network because it predicts the game winner. And AlphaGo Zero uses a Monte Carlo tree search that exploits this neural network for selecting moves during games of self-play. In order to understand some characteristics of AlphaGo Zero, we can compare it to AlphaGo Fun, which is considered to be the first program to achieve superhuman performance in Go. AlphaGo Fun uses two separate deep neural networks. The first one is a policy network that outputs move probabilities. This network is initially trained by supervised learning and then refined by a reinforcement learning algorithm. The second is a value network that outputs a position evaluation and is trained on games played against itself. The two trained networks are combined with a Monte Carlo tree search in order to provide a look-ahead search. On the other hand, AlphaGo Zero, proposed in this paper, starting from a random play, is trained only by self-reinforcement learning, with no supervision or no use of human data. AlphaGo Zero uses only the black and white stones from the board as input features, and uses only a singular neural network for both policy and value. And it uses a simpler tree search that relies upon this neural network to evaluate positions and sample moves. The new reinforcement algorithm adopted by AlphaGo Zero exploits look-ahead search via Monte Carlo tree search inside the training loop, and this results in a rapid improvement and in precise and stable learning. We are going now to explore the core of the method in four main parts: the neural network, the games of self-play, the Monte Carlo tree search, and the self-play reinforcement learning algorithm that is used to train the neural network. The neural network is a residual neural network f theta with parameters theta. It takes as input a board representation S composed of the current position and its history. The history is necessary because Go is not fully observable only from the current position because the repetitions are forbidden. Given a state S, the neural network outputs two values, the move probabilities P and the value V. The move probabilities P is actually a vector of move probabilities, and each item in the vector is the probability of selecting the move A given the state S. V is a scalar, and it's the probability of the current player to win from position S. The outputs of the neural network P and V from the state S can be seen as estimates of pi and V, where pi of S is a stochastic policy and it's a probability distribution over actions. And V is the expected value of following the policy pi in the state S. The Monte Carlo tree search uses the current neural network f theta to guide the simulations. Given the state S, it outputs probabilities pi of playing each move. Given these probabilities, it's then possible to select a move. In the tree, each edge is characterized by S, which is the state, and A, which is the action. And each edge stores a prior probability P, a visit count N, and an action value Q. The search has 3 stages. First of all, the algorithm traverses the tree from the root here to a leaf. In each node, it picks a child, and to decide which action to select, it uses an upper confidence bound, which expression we can see right here. In particular, it selects an action that has been better evaluated in past simulation, and this is given by the Q value, and an action that the policy network likes, and this is given by the U value, where the U value depends both on N, the visit count, and P, the prior probability. Once a leaf node is reached, the algorithm expands the leaf node and evaluates this node with a policy value network right here. So we can see the evaluation by the policy value network. And once the evaluation has been done, the algorithm backs up the evaluation of the value V in the search tree. So from here, in the third stage, from here it backs up the value of the evaluation up to the root. In particular, it updates the visit count N and the value Q, because in every node there is the mean evaluation for its edge Q. And in particular Q, the Q value stores the mean evaluation of what is found after, so like under the edge that we are considering for the Q value. Once the search has finished, the method outputs pi here, and so given this probabilities pi, it's possible to play, which is to select a move to perform. The Monte Carlo tree search is used during games of self-play in order to select the move to perform in each position S. The method is the following. It plays games of self-play S1 to S big T against itself. In each position ST, it runs a Monte Carlo tree search in order to select the move AT. The move is selected using the policy output of the Monte Carlo tree search pi T. At the terminal position S big T, the game winner Z is found. Monte Carlo tree search can be seen as a policy improvement operator because it uses the current value function to generate a better policy, since the Monte Carlo tree search selects better moves than the ones given by the current neural network. Self-play games with search and with the selection of the game winner that is used as value can be seen as a policy evaluation operator because it estimates the value function of the current policy. The self-play reinforcement learning algorithm runs games of self-play that use Monte Carlo tree search in order to select each move, and uses policy improvement and policy evaluation operators that we were talking about in the previous slide in an approximate policy iteration procedure. In particular, the policy improvement starts with a neural network policy. It executes a Monte Carlo tree search based on that policy's recommendations, and then uses the stronger search policy that is found in order to improve the neural network. The policy evaluation is applied to the stronger search policy, and the outcomes of self-play games are also used to improve the neural network. These improvements are performed by training the neural network parameters to match the search probabilities and the self-play outcomes. In the next slide, we are going to take a deeper look at the algorithm. Neural network weights are initialized randomly to the value θ0. At each iteration I, games of self-play are generated. Monte Carlo tree search uses the previous neural network f theta I-1, and data from each time step t of the games st, pi t, and zt are stored. The neural network f theta I is trained from data s, pi, and z sampled uniformly from time steps. And the neural network parameters are trained using gradient descent. They are updated to make the move probabilities and value p and v match the improved search probabilities and self-play winner pi and z. In particular, the loss function showed here in the slide, L, minimizes the error between the predicted value v and the self-play winner z with the mean squared error here, and maximizes the similarity of the neural network move probabilities p to the search probabilities pi in a cross-entropy loss term here, and then a regularization on the parameters is added here. New parameters are used in the next iteration of self-play in order to make the search even stronger. The three components of the self-training pipeline are all executed asynchronously and in parallel. First of all, optimization. The neural network parameters are continually optimized using recent self-play data. Each batch of data is sampled uniformly and at random from all positions from the most recent 500,000 games of self-play. The neural network parameters are optimized using stochastic gradient descent with momentum. The optimization process produces a new checkpoint every thousands of training steps. This checkpoint is evaluated by the evaluator, and it may be used for generating the next batch of self-play games. For the evaluation, AlphaGo Zero players are continually evaluated. Each neural network checkpoint is evaluated against the current best network before being used for data generation. The neural network is evaluated by the performance of a Monte Carlo tree search that uses the neural network itself to evaluate leaf positions and probabilities. Each evaluation consists of 400 games, using a Monte Carlo tree search with 1,600 simulations in order to select each move. For the self-play games, the best performing player is used to generate new self-play data. In each iteration, the player plays 25,000 games of self-play, using 1,600 simulation of Monte Carlo tree search to select each move. In order to evaluate the method, the AlphaGo Zero model tested is a 20 blocks ResNet. The training took 3 days, with around 4.9 million games of self-play generated during training. The player runs on a single machine in the Google Cloud with 4 TPUs, although it could also have been distributed. Here we can see some results of the empirical evaluation. In figure A, here we see the performance of AlphaGo Zero during self-play reinforcement learning as a function of the training time measured on an ELO scale. We can see that the learning progressed quite smoothly during training, and it didn't suffer from catastrophic forgetting or oscillations. AlphaGo Zero is compared to the same neural network architecture but trained with supervised learning, and is also compared to AlphaGo Lee, a previous AlphaGo player. We can see that AlphaGo Zero outperformed AlphaGo Lee after just 36 hours of training. Just for comparison, AlphaGo Lee was trained over several months. The AlphaGo Zero player, obtained after 72 hours of training, was set to play against the version of AlphaGo Lee that was used to defeat Lee Sedol, which is a Go game champion. And just to have an idea of the computational resources, AlphaGo Zero used a single machine with 4 TPUs, whereas AlphaGo Zero Lee was distributed over several machines and used 48 TPUs. AlphaGo Zero defeated AlphaGo Lee by 100 games to 0. From figure A, B, and C, we compare AlphaGo Zero to the same neural network trained with supervised learning. The supervised neural network achieved a better initial performance and a better outcome prediction at the beginning, but was later surpassed by AlphaGo Zero. The supervised neural network was always better at predicting the outcome of human professional games. From the results, we can note that although supervised learning achieved a higher move prediction accuracy, the self-learned player performed better overall and defeated the human-trained player within the first 24 hours of training. This suggests that AlphaGo Zero may be learning a strategy that is qualitatively different from human play. In order to separate the contribution of architecture and algorithm, the performance of different choices for the neural network are compared. The paper tests different combinations of the neural network architecture between residual neural network and convolutional neural network, and of the choice of single or separate neural networks for policy and value. According to the results shown in this graph, using a residual neural network provides more accuracy, achieves a lower error, and improves the performance of the AlphaGo player. Combining policy and value together into a single network slightly reduces the move prediction accuracy, but reduces the value error and boosts the player performance in AlphaGo. The final AlphaGo model uses a 40-block ResNet and was trained for over 40 days. In Figure A, we can see the learning curve that shows the performance of each player during training using an ELO rating, and the performance of different programs for Go game, again compared using an ELO rating. In particular, we can see that AlphaGo Zero outperforms both other AlphaGo players, shown in blue, and other previous Go programs, shown in red, and also the outperforms the use of the raw neural network alone, shown in gray. A question at this point could be, what does AlphaGo Zero learn? Results suggest that AlphaGo Zero may be learning a strategy that is qualitatively different to human play. It discovers quite a good level of Go knowledge during its self-play training process. And this includes both fundamental elements of human Go knowledge, but also non-standard strategies beyond the scope of traditional Go knowledge. The advantages of the proposed method are that it learns solely from self-play reinforcement learning, starting from random initial weights without using rollouts in the Monte Carlo tree search, with no human supervision and using only the board, state, and history as input features, and using the minimum amount of domain knowledge. The algorithm is able to overcome in performance both human and supervised learning systems. In conclusion, AlphaGo Zero demonstrates that a pure reinforcement learning approach is fully feasible, even in a challenging domain such as the one of Go game. Indeed, it's possible to train to a superhuman level without human examples or guidance, and given no knowledge of the domain beyond basic rules. And it requires just a few more hours of train and achieves much better asymptotic performance when compared to training on human expert data. In the space of a few days, starting tabula rasa, AlphaGo Zero was able to rediscover much of the human Go knowledge, but also to discover novel strategies. Thank you very much for the attention, and now some questions if something was not clear or if you want some clarification. Thank you.